In a double slit interference experiment, a light source emits two wavelengths. One lambda equals 430 nanometers. Let's call it lambda 1, and lambda 2 equals 510 nanometers. We know that the slits are separated from the screen by a distance of 1.50 meters. So let's call it R equals 1.50 meters. And the slits are separated from each other by 0.025 millimeters. So let me draw the experimental setup for a moment so you can remember the picture and the notations. But we have to remember that we have two different wavelengths, so I rather take it draw it greenish and bluish, because one is like 510 is probably in a range of green bluish, and 430 is a blue violetish. Let me change that. So now we're asked to find a separation distance between the third order bright fringes for the two wavelengths. So if this is m equals 0, m equals 1, m equals 2, m equals 3. So we have one is not necessarily purple, but the purplish third order from here to here. That would be y, let's say 1, and the other one will be y2 for the second wavelength. So we want to find out the difference between these two positions. Okay, so we want to find this little one, let's call it delta y. So if I want to write that down, that would be, I want it d delta y equals y2 minus y1, and we are looking for the third bright fringe, and trying to find the separation between the positions between these two bright fringes. So that's what is the question mark for us. Now, to find a position, we know that the expression y for mth bright fringe should equal rm lambda over d. So for us, for the first lambda 1, okay, so y1 equals r times 3 times lambda 1 over d. For lambda 2, y2 equals r 3 lambda 2 over d. Now from these two we can find the delta y equals r over d. That would be lambda 2 minus lambda 1. All we need to do, plug in the numbers that we have, and let's not lose that. So that, let me just write it in here. So delta y equals 3 times, the r is 1.50 meters, divided, the separation of the slits is 0.025 millimeters. So let's convert it to meters, times 10 to the negative 3 meters, and times lambda 2 is 510 nanometers, so convert it to meters. So 510 times 10 to the negative 9 meters minus 430 times 10 to the negative 9 meters. That will give us 0.0144 meters, which is 1.44 centimeters. Now, there is an interesting question raising. It's like, is there any spot on the screen where these two bright fringes from these two wavelengths will exactly overlap? Well, if we want to find such a location, we will need to make these positions of each fringe from each wavelength equal to each other. So I could say y1 equals y2. But here's a tricky moment. This y1 is generated, this is the bright fringe from the lambda 1. So I can write r times m lambda 1 over d. The tricky moment here is that the second one doesn't necessarily have to have the same order of bright fringe. So in other words, like the third bright fringes, we know they don't overlap, but can fifth bright fringes overlap? Maybe not. So what we want to find out, maybe the 10th bright fringe from lambda 1 and then 25th bright fringe from lambda 2 overlap with each other. Take a moment to think about it. Pause this video for a moment and see if you really understand what it is asking. So that's why I'm gonna have M1 because the orders are different, and that equals R, a different order bright fringe from lambda 2 over D. So from here, the r's will cancel out, and we will end up having an expression m1 lambda 1 equals m2 lambda 2. So from here, I can say m1 over m2 equals lambda 2 over lambda 1. Where lambda 2, let's go recall what was it. For lambda 2, we had 510 nanometers. For lambda 1, 430 nanometers. Let's plug that in here. So 510 nanometers divided by 430 nanometers, which makes it 51 over 43. So we end up having m1 over m2 equals 51 over 43. What does this mean? It means the 51st fringe of 430 nanometer wavelength will overlaps with 43rd fringe of 510 nanometers. Well, but this is not the end. We're asked to find a location on the screen. So which means we're asked to find, we want to find the y. For example, how do we find the y for example, a 51st fringe for 430 nanometers? So that we're going to use, it's a bright fringe, we're going to use our expression r m1 lambda 1 over d. So that equals what was our R? Our R was 1.50 meters. M1 is 51. Lambda 1 is 430 times 10 to the negative 9 meters over, and the separation between slits is 0.025 times 10 to the negative 3 meters, which equals 1.32 meters. So that is quite far away in the on the screen when you see the overlap. But there is a very interesting moment. This value 1.32 is quite comparable for the distance of the screen from the slits. And this time, if you check, let's say this is the double slits right here, okay, and then here's the screen. So from here to here is 1.50. Now we want to find out the separation. So 1.32 would be from somewhere here to here, 1.32, which means this angle is not anymore small angle. So remember our expression for positions we found just for small angles. So maybe this is not valid, not maybe, it is our expression that we used here is not valid anymore. For answering this question better, maybe we should start with the bigger diagram where this is my R, and that equals 1.50 meters, and here is my Y. I am using the bottom one for the space. So, and then this would be the angle theta, and for the bright fringe, we should use the original condition for d sine theta equals m1 lambda 1, and that equals m2 lambda 2. Well, from here our relationship is still valid, where we had what did we have here? m1 over m2 equals 51 over 43. So let me just write it here, m1 over m2 equals 51 over 43. So that is valid. Now from here, to find the y from this triangle, I can say y equals r times tangent theta. But then we don't have the theta. I will be using this top part of the top equation and from one wavelength, because I already have the value of m1, and find the theta. So from here I can write sine theta equals m1 lambda 1 over d, and theta from here equals inverse of sine times, well, m1 is 51. Let me just plug in the numbers right away, bring it a little higher. So here we have 51 times lambda 1 is 430 times 10 to the negative 9 meters divided by d is 0.025 times 10 to the negative 3 meters, and then plug this into a calculator. We will get the theta equals 61.3 degrees. Now we can take this 61.3 degrees and plug it in here. So y equals 1.50 meters times tangent 61.3 degrees. And so if we plug this one into calculator, we'll get 2.74 meters. Well, that would be the actual position where the two bands, bright bands, meet from different light sources, which is actually what we expected. Let's check our previous result, which was 1.32 and 2.74, which is way different. What is it? Almost twice further away. So in conclusion, we could say that the 51st fringe of the 330 nanometer light does overlap with the 43rd fringe of 510 nanometer light, but not at the location of 1.32 meters, but at the location of 2.74 meters. Thanks for watching. Stay tuned for more to come and have fun with physics.